In our fifth installment of Chapter 6, we're going to cover 6.12 and part of 6.13, which is revisiting the reactions that have been introduced thus far in Chapter 6, but considering the stereochemistry of the reactions, right? We're bringing that back from Chapter 4, where I'm sure you were happy to leave it, right? But we do have to consider these things in 3D. Okay? And we're going to be introducing a lot of important terms: regioselectivity, which we've already talked about with Markovnikov's rule, stereoselectivity, and stereospecificity. Okay, so reactions that are regioselective, stereoselective, or stereospecific. So make sure by the end of this video you know what those three terms mean. Okay. Stereochem, as you know from Chapter 4, is all about thinking about things in 3D. And so we have to ask ourselves, if I'm making a product with a stereocenter, meaning it can exist as two or more stereoisomers, does a reaction produce just one of them or a mixture of all of them? Or on the other hand, if a reactant can exist as two or more stereoisomers, do those stereoisomers make different products respectively, or do they make the same product? So let's jump in to consider those possibilities. Okay. Regioselectivity is the term we already know. Okay. We saw it when we were talking about carbocation stability in two possible products going through two different intermediates, different transition states. They had different stability, so one product was favored. Right? And that's regioselectivity. It can form two or more constitutional isomers, but one of them is preferred. And remember that something can be moderately regioselective, highly regioselective, or completely regioselective, where it only forms one of the isomers. Okay. So it's regioselectivity. Make sure you've got that jotted down. Constitutional isomers, where the bonds are different. A stereoselective reaction refers to the preferential formation of a stereoisomer rather than a constitutional isomer. Okay, so it's still the same type of selectivity, but it's preferentially forming one stereoisomer. Okay, so we don't have bonds in different places, but we have different stereoisomers, right? Could be cis or trans, or erythro or Threo, thinking about Fisher projections, and things like that. And again, things can be moderately, highly, or completely stereoselective. That's not to be confused with stereospecific. Okay. A stereospecific reaction is where I have one stereoisomer reactant that forms one stereoisomer product. Okay. So in a stereospecific reaction, the reactants exist as stereoisomers, and each of the stereoisomer reactants forms a different stereoisomer product, which is a little tricky, right? Stereospecific and stereoselective. Everything that's stereospecific is stereoselective, okay, because it's only forming one type of isomer. So everything that's stereospecific is completely regioselective, but not everything that's, so I think I just said regioselective. Everything that is stereospecific is completely stereoselective, 100 to 0. But not everything that's stereoselective is necessarily stereospecific. Okay, because as we just saw with something that's stereoselective, one isomer could form two products. If it's stereospecific, it's 1 to 1. Okay. And I might not even have a reactant that's a stereoisomer to begin with, but then it preferentially forms one stereoisomer. Okay. That's something that would also be stereoselective, but not stereospecific. Okay, so now that you heard the word stereo more than you thought you ever would in your life, let's think about the reactions again. Looking at this reaction here, an alkene plus a hydrogen halide. This reaction doesn't have any stereoisomers to worry about, okay, because I've got two alkyl groups, the methyl groups here, that are the same. It doesn't have an asymmetric center, so I don't care about the stereochemistry in this case. Okay. Putting the bromine here on carbon 2 means this reaction was regioselective, as we've covered in the past, but this was not stereoselective or stereospecific because there are no stereoisomers. Okay. Looking here now, Okay. This reaction is regioselective, and we formed an asymmetric center. So I have to ask myself what's going on with the stereoselectivity. Okay, so this is an asymmetric center because it's got 4 different groups: the hydrogen, the methyl, the bromine, and the ethyl group. Okay. But in this situation, you see on the top, the product is a racemic mixture. Okay. I get a mixture of R and S in this case. Right? And the question is why? Okay. Well, if I consider the reaction mechanism, right, it goes via a carbocation intermediate. Right, the first step is the addition of hydrogen to this carbon here, putting a positive charge on C2 there. And that carbocation intermediate, it's sp2 hybridized, the carbocation is planar, okay? Meaning the bromide nucleophile can come in and attack from either side of that plane, either above or below. Okay? And that's a good general rule. When a reactant that doesn't have an asymmetric center forms a product that has 1 asymmetric center, so we went from 0 to 1, it's always a racemic mixture. And so I'd jot that down in your notes. That's pretty easy to remember, right? Go from 0 to 1 asymmetric center, it's a racemic mixture, 50-50 R and S. Again, because it's trigonal planar, meaning bromine can come from the top or the bottom, right? And that forms 2 different products. One's S, one's R. And it's a 50-50 shot, right? Equal probability of where it's going to approach from. We would see the same thing, right, if I had E and Z isomers to begin with, right? E or Z, doesn't matter. When I go through, in this case, the acid catalyzed addition of water, okay, I went from 0 asymmetric centers to 1 asymmetric center. And again, I end up with a racemic mixture. Yep. Don't let that E or Z throw you off. 0 asymmetric centers, 1 asymmetric center right here with 4 different groups. You're going to get a racemic mixture. Okay, so that's easy. 0 to 1, always a racemic mixture. No exceptions to worry about. The tricky part of this chapter, right, is if you start to form a second asymmetric center. If you had 1 asymmetric center to begin with, okay, so we're looking at this carbon right here with 4 different groups. 1 asymmetric center to start off. Okay, and then I form a product with 1 new asymmetric center. So I went from 1 asymmetric center to 2 asymmetric centers. Okay. In that situation, right, your product's a pair of diastereomers. Because again, that new asymmetric center that was formed is a 50-50 mix of R and, sorry, I said that backwards, of S and R. So your asymmetric center from the beginning was unchanged. Okay. Nothing changed there. And then the new one that was formed here from this carbocation is 50% S, 50% R. Okay. So going from 1 to 2, that relationship is a pair of diastereomers. Okay. So if you go from 1 to 2, you get a mixture of diastereomers. Okay. Now the question becomes, right, if a reactant did not have an asymmetric center and I formed 2 asymmetric centers, right, what am I forming? And the stereoisomers depend on the mechanisms from these different reactions. Okay. So again, that's what we're going to talk about now, 0 to 2 for a while. If you go from 0 to 1, it's a racemic mixture. If you go from 1 to 2, it's a pair of diastereomers. What we're talking about moving forward is going from 0 asymmetric centers to 2 new asymmetric centers, like right here. Okay. Addition of HCl to this alkene formed now 2 brand new asymmetric centers. And the type of stereoisomers that we form depend, as I just said, on the mechanism. If you go from 0 to 2 asymmetric centers, and you go via a carbocation intermediate, you end up getting 4 stereoisomers, all 4 of them. Okay. And you should know by now in chapter 6 that the addition of HCl to an alkene occurs via a carbocation intermediate. So does the acid catalyzed addition of water. Okay. So in that case, right, because I could add the proton and get a positive charge here or here, and then it's again a 50-50 shot of the chlorine adding above or below after the hydrogen could add above or below. You end up with those 4 combinations of above and below, okay? Because in the first step, when you're adding the hydrogen electrophile, it can happen on the top or the bottom of the plane of this dimethyl cyclohexene here. So I had the hydrogen on the top or on the bottom, okay, above, below. So notice the difference right here on this slide. That's giving me different stereochemistry there. Then I've got that carbocation intermediate, again, planar right there. And then my chloride nucleophile can add above and below to that one, or above or below to this one. So it's 4 combinations of above and below, above, above, below, above, above, below, 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 right? And each one of those corresponds to the 4 combinations of R and S. Right? You can have RR, RS, SR, or SS. So that's why you get 4 possibilities, because these could occur via syn or anti additions, which are key vocab words from chapter 6. Okay, a couple more. We got 3 at the beginning: regioselective, stereoselective, and stereospecific. Here's another one: syn and anti additions. A syn addition is when your 2 substituents have added to the same side of the double bond. Anti-addition is when they add on opposite sides of a double bond. Okay. So let's take a look at what that means. Okay. Here I'm looking at a hydrogenation reaction, right? Palladium catalyzed addition of hydrogens, taking an alkene to an alkane. That only occurs via a syn addition. Why is that? Thinking about that palladium catalyst, right? Palladium on carbon, the alkene has to sit down on top of the surface of the metal catalyst where the hydrogen has already been adsorbed. And meaning those hydrogens can only be added to one side. Right? I've got H2, I've got my alkene, they have to come together side by side like that. So that can only happen by a syn addition. They get added to the same side. Okay. And if you have a syn addition to a cis isomer, you only get the erythro stereoisomers. And this is the part of the chapter where things really get convoluted, and I don't like the way the textbook approaches this. Yeah, so you can skip, if you've got the textbook with you or lecture slides, you can skip ahead and check them out. There is a golden rule that helps guide you through these that I want to introduce now. And you've got to figure out a way to remember this. Get it tattooed on your forearm if you need to. Okay. Can't spell. Right. It's this: cis, syn, erythro, or cis. That's the golden rule, or any combination where you change exactly 2 of those words. Okay. You can't change 3, you can't change 1. Cis, syn, erythro, or cis. So what is this telling me? If I have a cis isomer, which I have here, I'm looking at the cis isomer of this alkene, and I do a syn addition, the product here are the erythro enantiomers when I look at the Fisher projections. And if you don't remember from chapter 4, the erythro enantiomers are the ones where the hydrogens are on the same side. Okay. The opposite of that is the Threo, T-H-R-E-O. I don't get those where the hydrogens are across from one another. Okay, so I don't get those. I only get 2 of the 4 enantiomers. And the cis refers to if this thing was in a ring. So the reason for that is because only 2 stereoisomers, or sorry, the reason only 2 stereoisomers is formed is because it has to happen, the hydrogen addition, either both above, like we have here, or both below. And that corresponds, right, looking at the perspective formulas, to just 2 isomers. The hydrogens have to be on the same side because it happens via a syn addition. Okay. But if it was trans to begin with, if I changed that word to trans and I do a syn addition, then the product has to be the Threo enantiomers. So let's take a look, see if that's on the next slide here. No, is it on the next one? Yeah, here it is. Syn addition to a trans isomer forms only the Threo. I changed exactly two of those words. What I'll ask you to do in this class, right, is use that rule, cis syn erythro or cis syn cis, changing exactly two, to tell me what's an allowed transition and predict the stereochem of products. Okay. Jumping back to slide 103 here. If you have a situation where all 3 substituents on both carbons that were in the alkene are the same, you only end up with 1 product because that product, while it is one of the erythroisomers, it's a meso compound because it has a superimposable mirror image right here. So that's just one thing to be on the lookout for. If those 3 are the same, you end up with a meso compound. Okay, but that's easy then. You don't have to worry about the stereochem of the products. Okay. So here's a continuation of what we were already talking about. Okay. Here is an example where the things are cyclic. Okay, so I have an alkene as part of a ring here, right, in the cyclopentene. If I undergo a syn addition to something that was cyclic in cis, the products are cis. Okay, so cis, syn, cis. If I do, right, again, if the substituents are the same, you get a meso compound. Nothing new there, right? I guess I was getting a little bit ahead of myself, but always be on the lookout for that. Okay, if it's cyclic with an alkene, if that's the case, cyclic alkenes are always cis, okay, because these 2 bonds are on the same side. It's not until you get to cyclooctene and above, 8, 9, 10 carbons, that it's even a possibility to get trans. Okay? It's rare, but it's possible. So for the purposes of my class, you can always consider these rings to be cis, meaning if that's cis, if it's doing a syn addition, like we have the addition of hydrogen here, then the product is going to be cis. Okay? They're going to keep things on the same side, the hydrogens on the same side. If it's a cyclic alkene and it does an anti-addition, then the product will be trans, because we're always changing exactly 2 of those words to use that rule to predict. Okay. Looking right here, right, it was cis. Addition of hydrogen is syn, so I know my products are cis. So that concludes part of 5.13 because this video, or sorry, 6.13 because the video has gone long enough. Have this rule written down. There's a reason I kept it up on all these slides, because we'll continue to use it in the next video for the rest of the reactions that we've introduced in chapter 6.